Well, okay, guys. Again, sorry for starting speaking with Spanish with the speaker, but now we are going to start the next seminar with Nicolas Robles. First of all, I need to say that this seminar is going to be recorded, okay? And those that do not want to be recorded, please leave the meeting. With that said, hello, Nicolas. Thank you very, very much to be here. It's a very great pleasure to have you here, honestly. I think your talk is very interesting. And in fact, Nicolas, well, it's so many things, but starting working on quantum computing in New York with IBM, and now is joining Rand Corporation as an applied mathematician. And today he's going to speak about the Feynman-Kac formula on partial differential equations and the Brownian motion with quantum computers. With that said, really, thank you very much to be here, Nicolas, and that's all yours.
Thank you so very much for the invitation, Alberto. I'm realizing how tricky it is to start speaking Spanish and now making the switch to English.
Yes.
So we'll get used to as we go around, as we go by. Sure. This is joint work that I've done with my colleagues at IBM, with Hedayat Al-Ghazi, Amol Deshmog, Noel Ibrahim, Stefan Werner, and Christa Zufal. And you can see the reference. It's in the Quantum Journal, Volume 6, page 730. And I believe I'll have the reference here as well, which is free to download if you want to supplement some of the pictures. In fact, some of the pictures I might need to show you from the paper rather than from the presentation, but we'll cross that bridge as we move forward. Okay, so like Alberto was saying, there's many things going on, and towards the end, we'll talk about how to implement these things on a quantum computer. But first, before we even begin to talk about quantum computers, I have to describe a little bit what it means to talk about differential equations, what it means to talk about stochastic differential equations, and what Brownian motion is. Okay, so what is Brownian motion? Something like 200 years ago, it was observed that if you throw a little bit of pollen into a glass of water, that pollen will have motion that seems to be random. Okay, the pollen gets bombarded by the water molecules, and every time you throw in pollen, the motion is never exactly the same. So it seemed to be random. And only in the turn of the 20th century was it understood by Albert Einstein and others that that this Brownian motion is a fundamental, feature of the universe. And he used Brownian motion to prove that molecules exist. And now we take this for granted, but back in 1905, it wasn't clear at all that atoms and molecules existed. And there was a lot of there was a lot of reservation about this idea, and Albert Einstein used this successfully. And I encourage you to check his papers because they're really interesting, to show that that one can compute Avogadro's number and things like that. However, the sound mathematical foundation for Brownian motion was not given until a quarter of the century into the 20th century by Norbert Wiener. And I'll tell you more about it soon. So what is exactly a stochastic differential equation? What is a Brownian motion? So Brownian motion is an index processed WT, and T runs through the real positive numbers, okay? So it's a stochastic process, and every time that it has a label T, it has a different number, like a different value. And it satisfies three properties. One of them is that the increments are going to be independent. If T is greater than S, then the difference between WT and WS is independent of whatever might have happened in the past. The increments are normally distributed. So W of T minus W of S has a normal distribution with mean 0 and variance T minus S. And the paths that this Brownian motion is going to follow are going to be continuous as a function of T. Okay, so these are the three things that characterize Brownian motion, essentially. Okay, so here's a picture of Brownian motion. 500 pictures, I think. Brownian motion, let's say that it starts at 0, which is my choice. And at every time step, it's going to take a value from the normal distribution, right? So I think I've plotted something like 500, and you can see that indeed they're normally distributed. You see the bell-shaped curve. It's very unlikely that one of these Brownian motions will hit this value, and also very unlikely that it will hit this value. We will most likely, if you start at 0, end somewhere near 0 as well. Okay, so there is something very important to say about Brownian motion, and it exists. You should never take it for granted. It's a very deep result in stochastic calculus and measure theory. The existence of Brownian motion has to do with the continuity of paths. These two things are okay. You can impose that in your definition, but that does not mean that is going to be necessarily compatible with the continuity of paths. So the fact that these paths were shown to be continuous was shown by Norbert Wiener in 1923. And our best tool to deal with Brownian motion is called quadratic variation. And one informal way of talking about quadratic variation is that if you take an infinitesimal little bit of Brownian motion and you square it, then it scales like time. Okay, and anything else will scale like 0. So if you take Brownian motion and you multiply by time, or you take time and you multiply by Brownian motion, or if you multiply time with itself, it scales like 0. But Brownian motion square scales like time, and this will come in very useful soon. So now there's what a colleague of mine likes to call the bestiary, the zoo of Brownian motion properties, and it's a very unusual function. First of all, we said it is continuous, but that doesn't mean that it's differentiable. In fact, it is continuous at every point, but it cannot be differentiated anywhere on the real line. And it's not monotone at any interval either, no matter how small that interval is. It will always be increasing and decreasing, increasing and decreasing. You cannot find the small interval for which it is monotonically increasing or monotonically decreasing. So that's very difficult to kind of picture. It has infinite variation. It has this quadratic variation that I was telling you about. If it means anything to you, it's a martingale. If it doesn't mean anything to you, then don't worry about it. It's not going to be important today. It is a Markov process, and it is also a fractal. So you can zoom in and you can zoom out of Brownian motion, and you will never see a structure because it's still, fractal nature. Okay, so let me get to the point. What is a stochastic differential equation? Okay, so colloquially, it's a differential equation that contains Brownian motion in it. So for example, if you let x of t be a stochastic process, and let's say that is governed by this SDE, d for differential of your stochastic process, some kind of deterministic function times t, plus some other kind of deterministic function times the d of wt, so the differential of Brownian motion. It cannot be differentiated, but you can still speak about differentials. So if g were 0, then this term would disappear and you would be left with only this part, and that would be an ordinary differential equation. There's nothing random about it, but it's because of the presence of this term that it makes it be a stochastic differential equation. So a very popular one that you might see in finance frequently is called geometric Brownian motion, and the idea is to make f be a constant times xt and g be another constant times xt. So this constant is called mu, and this other constant is called sigma. Mu is called the drift, and sigma is called the volatility. And it is widely accepted in finance and economics to be a reasonably good model for stocks and other assets such as equities. And with high technology, such as Ito's lemma and so on and so forth, you can actually solve this stochastic differential equation. It's unusual because not most SDEs cannot be solved, but this one can be solved. And if your initial price, your initial value is x0, then the solution is given to you by this. Now, x0, if it is positive, let's say it is positive, and this exponential will always be positive because exponentials are never negative. So x of t will always be positive. It will never be 0 or negative. So this is what it would look like. If we say that the initial price is $1 or €1, then this is going to be your geometric Brownian motion. Okay, it's not going to be normal necessarily because it's skewed to one side. It's going to be log normal. And it's an acceptable model for stocks and equity because stocks and equity never go below 0. If I own IBM stock and IBM were to, I don't know, collapse or go default or bankrupt, then the value of the stock would be 0, but it would never go below 0. So that's why it's an accepted model for stocks. Any questions so far? Okay, please feel free to ask me questions as we go by. So there's a great source of confusion. I was certainly confused at the very beginning. The solution of an SDE is a stochastic process, x of t. So here's an SDE, and here's the solution. Every time you instantiate the solution, you're going to get a different path. Okay, so because it's a stochastic process. And the solution of a partial differential equation is a deterministic function that never changes. Like that is set by your boundary conditions, etc. Okay, so that will never change. So there is a way to script this. This Python script that I wrote, and I can share with you if you want, in which I am taking values from the normal distribution at with mean 0 and variance 1, and I'm appending them in a path. And here you can see how I'm scaling with the square root of time as per Ito's lemma, right? Brownian motion scales like the square root of time. So that's exactly what makes it be so jittery. Okay, so here's two examples of this Brownian motion. I think at the time IBM was trading at $140, and the interest rate were 3%, and the volatility was 25%. So this is two typical paths that the stock could take. Okay, and they're both equally valid. They're both different instantiations of Brownian motion. Okay, so what does this have to do with PDEs? Wasn't the solution of a PDE deterministic? Yes, that is true. Okay, so here, this is what it has to do. Suppose you have a Wiener process, x of t, and you have the simplest kind of SDE that you can think of. D of xt equals dwt. Okay, that is so-called pure Brownian motion. Okay, there's no drift. There is, the volatility is set to 1. There's just nothing in it other than that. And suppose that c is a reasonable function. Let's say it's continuous, differentiable. There's nothing pathological about it. Okay, then we define the conditional expectation of, so Brownian motion goes from 0 to capital T. So capital T will be the end of time for us. And at capital T, we use our test function psi and act this function on the last values of the Brownian motion. Okay, and we are conditioning on x of t for any t between 0 and big T to be x. Okay, and this will be called the function u of xt. If we define this and we use the properties that I talked to you about earlier on Brownian motion, and we use Ito, and we use some clever mathematics, it can be shown that u of xt is equal to this integral. Okay, and everything here was a stochastic because this is the expectation of a stochastic process, but everything here is deterministic. There is nothing, and all these values are set, and this is a function of your choice. Okay, so you've gone from something, you've taken the expectation of a stochastic process and you've shown that it is deterministic. So what do I mean by this? So for example, if I take psi of x to be the Dirac delta function, then my integration, when I replace this by a Dirac delta function, then this becomes the Gaussian curve, and this is the plot of the Gaussian curve. So what do I mean? Okay, let's see. Let's do an inspection. So we said that u of xt was equal to this conditional expectation, and through some clever mathematics, we turn it into this integral. If we take the partial derivative with respect to t, and the second order partial derivative with respect to space, respect to x, and we multiply by a half, then we see that it's equal to the negation of the partial derivative with respect to t. So this function satisfies this partial differential equation. And this is what I like to call the baby version of Feynman-Kac. Okay, so this satisfies a differential equation, partial differential equation. So there's two ways of going about it. And it does say something about your personality. You can go ahead and simulate the paths a lot of times and then take the average of the paths, or you can solve a differential equation to find out the expectation. So how does this kind of scale in a not so baby version? Now, instead of having your pure Brownian motion, now I'm going to add the coefficients as well as a drift. So my drift is going to be 2 times some function a and the square root of that. I will motivate the square root shortly, plus a drift. And my conditional expectation now is going to be a little bit more convoluted, but essentially the same. Instead of C, I think I'm going to call the function F. I probably should have called it C to be consistent, but never mind that. And this expectation, you can find it. What is C? Oh, C is another function of your choice. I think for me, C was 0. So the integral of 0 is 0 and the exponential of 0 is 1. So that's why I didn't see that term earlier. You know, this expectation now, it can be found by simulating a very large number of Brownian motions that obey this stochastic differential equation and then taking their average. So it can be done with a Python script that I was telling you about, or it can be found deterministically by solving this PDE with the final condition at the boundary that at the end of time, at capital T, you must satisfy this boundary condition f of x. Okay, so let's look a little bit closely at this differential equation for a moment. Okay, this is the one that I'm basically recopying this one right here. Okay, so let's have a look. This is an example of something called second order parabolic differential equation. And it might ring a bell. It might ring a bell, you might have seen it before. So let's say that, for example, special case a of x equals -1 and b of x equals c of x equals 0, then you are left with, this is -1, this is 0, and this is 0. Okay, so I am left with the heat equation. And this is a linear L1 normalizable PDE. So it means that the solution U, when you integrate it with respect to the L1 norm, is going to integrate to 1. Okay, so the solution of this is a probability distribution function, as it should be. Now, let's suppose now that a of x equals 1/2 of some constant square times x squared, and b is equal to some constant times x, and c is that constant r. Okay, and now for cosmetic purposes, instead of x, I'm going to call it s, capital S for stock, and the solution u, I'm just going to call it capital V, just because the literature is more common with this notation. If you do this, then you obtain the Black-Scholes equation, which is the kind of cornerstone for option pricing and derivative pricing. And if you choose, for example, this boundary condition at the end, S minus K, where K is something called a strike, then you would be pricing a European option. If you choose, for example, not the last price, T, I guess this should have been S of T here, but instead of using the last price, you use the average of the prices throughout the lifetime of the option, minus the strike, and you compare it against 0, and you take the bigger of the two, then you will be pricing a more exotic option called an Asian option with strike K. Okay, so I've gone from Brownian motion, and I've been able to get the heat equation and the Schrödinger and the Black-Scholes equation. Now, check this out. Suppose I perform the so-called Wick rotation, and I change T for -I tau, where I is the square root of -1, and I add this funny looking h bar constant, you know, which I'm not motivating, but it doesn't matter. And I say that a of x is equal to some constant, h bar squared divided by 2m. I turn off the middle term, and instead of calling c of x the function that appears in my PDE, I call it v of x, capital V of x, for a potential. Again, purely cosmetic. And instead of talking about u, I'm going to call this psi. And then I don't want to see everything in terms of tau. I'm just going to do another cosmetic change, and I'm going to replace tau by t. Then I'm going to get this differential equation over here. And this is the Schrödinger equation that we all know and love. Okay, this is very different from the heat equation because it does not have an L1 normalization. It has an L2 normalization. When you take the solution of the Hilbert of the Schrödinger equation, you put the absolute value and you take the square, then that integrates to 1 because it's an amplitude. Okay, and your particle or whatever quantum system that you're looking at depends heavily on the potential. Okay, so I can do a little cosmetic change, and I can leave this as is, but I can factor out everything not having to do with the wave function, and I can call it h as a differential operator, and this will be my Hamiltonian. Okay, so I started with Brownian motion, and from Brownian motion and Ito calculus and all of these things, I've ended up with the Schrödinger equation. Why is this important? Because when you put it all together, everyone's been getting the same Nobel Prize, in my opinion. So Schrödinger got the Nobel Prize in 1933 for the Schrödinger equation. Feynman, and we'll talk about Feynman-Kac in a moment, he also got it indirectly through the path integral method in 1965. Samuelson got the Nobel Prize in economics for suggesting that Brownian motion, geometric Brownian motion, was a good model for stocks. And Scholz and Merton, because Black had already died, also got the Nobel Prize in economics in 1997 for a different manifestation of the Feynman-Kac formula. So everyone's been doing the same thing, and it's obviously important because everyone gets the Nobel Prize for it. Okay, so, and this is also something that is touchy. People feel very differently about these kind of interpretations of quantum mechanics. If you ask around, if I were to do a survey, what is your favorite interpretation of quantum mechanics? Most of you would probably answer Copenhagen. Some people, like my supervisor, would say the many worlds or many minds, the Everett interpretation, and so on and so forth. Maybe some of you would, for information theoretical. I think that it's personally none of these. There is another interpretation of quantum mechanics that I think it gets overlooked a lot. Oops, let me make this a little bit. And it's called stochastic quantum mechanics. Okay, so I encourage you to check this out on Wikipedia. It has to do with quantum foam. And I think at the heart of space-time, everything is Brownian motion. And you are only seeing the manifestations of Brownian motion through the Schrödinger equation. And then the Schrödinger equation becomes the Hamilton-Jacobi equation and Newton and all of these things. So yeah, it's easy to get lost in these ways of interpreting quantum mechanics. All right, so what did we do in our paper? This was very well understood for one dimension. So we started by considering a d-dimensional stochastic process where we have up to capital D Brownian motions and capital D stochastic processes and a vector of Brownian motions up to capital N. And instead of having one single Brownian motion or one single SDE, I'm having now a system of SDEs where I ranges from 1 to D. Okay, and each one of these SDEs can have up to N Brownian motions. So there's a lot of forces, there's a lot of moving parts, and different Brownian motions pulling in different directions according to the strength given to them by this correlation factor and so on. Okay, so in this case, essentially you're still gonna get a differential equation of PDE, but it's higher dimensional, and the generator or the differential operator that appears in this differential equation is going to be a sum of a lot of partial derivatives, mixed, and some of them single. Okay, and your Brownian motion, your expectation or your conditional expectation is going to be over a vector. Okay, because it's this X is a vector. It has how many did we say? D for dimension, I suppose. Okay, and the Feynman-Kac formula in this case, when you go through the mathematics, is going to be this differential equation with one single T and G acting on U minus some discount factor if you want. Usually I set R to be 0 so that this is easier to handle. And you can have an initial condition or a final condition. If you're doing finance, you usually have a final condition. If you're doing physics or chemistry or something like that, you're going to want to have an initial condition. So I'm going to set it at the beginning of time. I have to start with this psi function. Okay, fair enough. So I'm going to take 2 dimensions and 2 Brownian motions per dimension. So I'm only going to have 2 equations. And the first one is going to be, okay, here's my drift. And like I said, there's 2 Brownian motions. And here is exactly the same, but with different coefficients. I'm going to set the drifts to be 0 for simplicity, because there's a lot of bookkeeping otherwise. And I'm going to set these correlations to be 1, 0, rho, and square root of 1 minus rho. Rho is a real number that is upper bounded by 1 and lower bounded by -1, and the interpretation of this rho is the correlation between the 2 Brownian motions. And this R that I was telling you about, I'm also going to turn it off because it's very annoying to keep it around. And I'm not going to talk about x1 and x2. I'm going to talk about x and y because it's It's easier on the eyes. Okay, so when I do that, then my differential operator is going to, instead of being this monster here, when d equals n equals 2, then it's going to simplify to something much nicer. It turns out to be Hermitian. I wasn't necessarily trying to get something Hermitian, but it does become Hermitian. There is double derivatives here, second order derivatives here, and here as well. Okay, and this will be my PDE, and my initial condition is that I want to be a product of two Dirac delta functions. One center at x0 and the other one center at y0, so that in a two-dimensional plane, I know exactly where I'm going to start. Okay, so as I said, there's two ways of doing this. You can either generate a lot of Brownian motions and take the expectations, which amounts to this kind of binning, or if you are kind of skilled with the differential equation systems and so on and so forth, you can try to solve this differential equation over here. And when you solve it and you plot the solution, you're going to get this bell-shaped thing. And you can see that, if I were to superimpose them, they would be identical. Well, if I took like an infinite number of samples, but the more samples I take, the more this is going to approach this. The correlation between them was a third. That was my choice. I can choose anything I want. Okay, so that's a long discussion on the prerequisites. Now let's talk about quantum computing and how to simulate these sort of systems and solve these sort of differential equations. And why would you want to do that on a quantum computer rather than on a classical computer? What is the advantage of the game? Now, suppose you have a time-independent differential operator, capital E, and this E is acting on n qubits, and it propagates. The evolution operator is going to be the expectation of minus I, E, T. Think of E as a Hamiltonian, if you wish. So provided that this Hamiltonian E is Hermitian, the quantum real-time evolution is going to be unitary. So if H is Hermitian, then this operator is going to be unitary, and you can decompose it into gates, and these gates are going to be reversible, and it's going to lend itself very well to a quantum computer, because you want all of your gates in your quantum system to be reversible and unitary as they should. However, here we are in a situation where we are applying this Wick rotation, and we are not going to be dealing with minus I necessarily, but we're going to be dealing with -1. Okay, so now this will not be unitary. It doesn't matter if H was Hermitian or not. If it is Hermitian or if it's not Hermitian, this is very unlikely to be unitary. So you are going to have to pay this price, and you're going to have to keep things artificially normalized as you go around. I'll tell you how we do that later. Okay, so excuse me. Suppose we are given an initial state, psi 0, in your registry of qubits. Then the normalized time evolution is going to be defined by this evolution operator acting on your initial state, and some alpha of tau that is going to keep this L2 normalized. Okay, and this might be an expensive thing to realize, and it might ruin your advantage if you're not careful. And the corresponding Wick-rotated Schrödinger equation for your system is going to be something like this, where lambda tau is another factor that ensures that things stay where they need to be, L2 normalized, because this thing is L1 normalized. Okay, so VARKite stands for variational quantum imaginary time evolution, and it's an algorithm to approximate quantum imaginary time evolution. So instead of evolving all the quantum states in the full Hilbert space, which is very large, by the way, what we do is we take a guess of what the solution might look like, okay, parameterized ansatz. And there's kind of optimization rules to make these ansatz to make these ansatz look within the whole Hilbert space, to look for what you're looking for in an interesting part of the Hilbert space, okay? And this optimization is called the McLaughlins variational principle. So you're letting go of a lot of room in your Hilbert space, exponentially much room. So you're making like some compromise there, but on the other hand, it will be much easier to use these ansatz and try to look for what you're looking for with it but sometimes you might not always find it. Oops, we do not want to restart my computer. Okay, so more precisely, instead of considering the general state psi of tau, I'm going to encode things into a vector, theta vector. Okay, and I might have up to n, capital N elements. It has nothing to do with the previous n, by the way. So it's an integer, and this integer will depend on the ansatz on your circuit, and I'll show you the circuit later. The choice of these ansatz is actually crucial. You want to do this in an intelligent way. Not all ansatz are as good as, like, certain ansatz are good for chemistry, some others are good for machine learning, some others are good for optimization, and so on. So there's a whole library in Qiskit about different ansatz and how to use them. So you want to be optimal about it. Okay, so when we were in on normalized situation, there was no alpha here. It was just like a Schrödinger, something that wants to look like the Schrödinger equation, but it's not, because the I is missing. But for the sake of explaining how the ansatz works is good enough. So the ansatz now is going to be, so I should have said this a little bit more explicitly. These thetas, theta stands for angle. These are the angles that are going to be fed to your rotation gates. Okay, so at every time tau, I'm going to have to know what the angles are so I can feed them into the circuit again. Okay, so this means that if you start with a registry of all your qubits and qubit registry, all of them at 0, then I'm going to apply a sequence of gates, G, on my ansatz on my registry of 0 qubits. And within that, there'll have to be some gates to accommodate for the normalization of L1 to L2 norms. So alpha is going to be a dictionary that allows me to talk about L2 norms from L1 norms. Okay, so G is the product here of n parametric unitaries, gates, if you wish, each composed of rotation gates. Not all of them will be rotation. Some of them might be X or Toffoli or Hadamard gate, something without necessarily an angle. Okay. So to produce Barkite, to produce the Barkite evolution, then we need to replace this unnormalized system by the ansatz in the PDE by first mapping the dynamics of the quantum state in the full Hilbert space to the dynamics in the smaller sub-Hilbert space of the ansatz. Okay, and the tool here that you want to use is called McLaughlins Variational Principle. And it tells you that if you take the ansatz, so if you replace, basically, if you come here and instead of looking at the full solution, you look at the ansatz solution, then you take the L2 norm of this and you take a variational, an infinitesimal variation of this and you set it to be 0, then that will be the smallest error that you can make. You're minimizing the error essentially. And when you solve this system of equations here, then you're going to obtain these so-called Euler-Lagrange equations, okay? And you're going to lead this time derivative on the vectors is going to lead to theta dots, first order ordinary differential equations. But you're going to need to know what these matrix elements are, and you're going to need to know what these vector elements are. And I can tell you, you can go through the literature, it's not too hard. The matrix elements are going to be given to you by this bracket. So you're going to have to take partial derivatives with respect to the two different thetas. This bra and this ket, you close it, and you'll obtain, and you multiply with the normalization factor, take the real part of this, and this will fit the elements of your matrix. And the elements of the vector are also very similar, except that you have a bracket here with the Hamiltonian in the middle. And it's a little bit more skewed because the derivative is in just one of them, not in the other one. And these you can find with a little bit of work. In fact, there is a quantum circuit that gives you these derivatives, so you don't have to do it by hand. Otherwise, it would ruin the whole idea of doing this on a quantum computer. So this quantum circuit evaluates this kind of bracket. And here is where I have to get the shape of this derivative. And here in the B, I have to get the shape of the other derivative, or for example, this and that. That will be okay. And you measure in the Z basis. Okay, so and because these things are made of gates already, differentiating a gate provides another gate. So if you differentiate a rotation gate, you're gonna get a prefactor times another rotation gate. So it just makes the circuit longer, but not more complicated. You don't have to introduce any new gates or anything like this. You just have to introduce more of the same gates. Okay. So one thing I'm not saying, I don't want to capitalize too much on this, but you might have to include the so-called phase fixed terms in order to keep, remove unwanted phases from the whole calculation. But that is an aside. How do you go from one time step to another? So in order to go from tau to tau plus delta tau, what you do is you take the previous set of angles and you add to it the time increment times the first order derivative. This is called the forward Euler method. So if we go back to these equations here, you can solve for theta, and in order to theta dot rather. And in order to solve for theta dot, you're going to have to invert this matrix and move it to the other side of B. So that's exactly what we're doing here. We're going to invert the matrix and multiply by B and multiply, well, this is matrix multiplication and this is scalar multiplication by the time step. So McLaughlins principle defines a unique order, ordinary differential equation, and you can solve it numerically. And you're going to have to discretize the number of time steps and so on and so forth. Bread and butter. If your matrix M is not well conditioned and you're inverting a singular matrix, then there is a technique from Moore and Penrose, since we were talking about Penrose earlier, to use the least squares to make sure that you can actually take the inverse of a singular matrix, but that does not need to concern us too much today. Okay, so different manifestations of Feynman-Kac will get you into different situations where the PDE might correspond or not to the different probability distributions. I do not know what happened here. We need to map these probabilities to amplitudes. So quantum states have to be normalized, like I've said it many times, with respect to the L2 norm. But probabilities come to you on the L1 norm. So this might hurt your eyes when you see it the first time. Every time you have a tilde, it means that you're not normalized. And you are coding probabilities directly into the amplitudes. Okay, so this is literally a probability. Okay, that is not how you would normally do it. Normally, you would have a square root of a probability in here. But because you don't have that kind of evolution today, you're going to have this alpha factor here to make sure that this changes from 2 to 1. Excuse me, from 1 to 2. Okay, usually this is what you would see. Square root of a probability. This would make it an amplitude. And the dictionary to speak from 1 to 2 or 2 to 1 is this alpha t. So you take the probabilities, you square them, you add them. Well, you add the squares rather, and then you take the square root of that. So that is your conversion factor. Okay. Let me see how I'm doing on time. Okay. So with quantum computers, you cannot ever get the full solution of anything, really. You can only get observables. So for example, if I'm doing HHL, and HHL says that, if HHL says you're solving AX equals B, like A is a matrix, so you're solving AX equals B, and A is a matrix, X is a vector, B is a vector. When you do this classically, it's very expensive to do this classically, but you get the solution as a vector. Let's say X1, X2, all the way up to, I don't know, Xn. So, okay, so it's expensive, but you get what you paid for. If you do HHL, for example, you're going to get the answer faster, but you're only going to get observables of the answer. So in your answer will be coded in some ket, and you might want to get an observable O. Let me put it with a hat. Okay, it's an operator. So you might get something like let's say X O of X. So if O, for example, is the identity operator, then what you're going to get from a quantum computer is this. And that is the average of X. So you're not going to get necessarily the vector. Maybe I should put it with that if you want. Matrix. Vector. You're not going to get this whole list. You're just going to get the average of the list. And if this is, I don't know, standard deviation, then you're going to get the standard deviation of your vector and so on and so forth. The same happens again with PDEs. That I will not get the full solution of the PDE, but I will get the most important things about this solution. So I'll get the moment, I'll get the first moment, second moment, third moment, fourth moment, and maybe I can reconstruct the whole function from its moments. Okay, let me move forward. I think I'm gonna skip this a little bit because this was just a little bit too difficult. So there is a way to recover the moments, and the moments have to, you have to encode your function f, that is the solution of your PDE, within the within your registry. And these moments, yeah, individually they're not accessible, but collectively, globally, you can access them. Okay, and there's a technique with weighted sums of operators that allows you to do this. Don't want to get too much into it because I'm realizing that I have too many slides, but you can do it. And you can do it with an accuracy that is up to you. So it's arbitrary. And you can, for instance, use a Hadamard test. Thing with the Hadamard test is that it was going to use a lot of samples, 1/epsilon squared, where epsilon is your accuracy. Or, so yeah, it's not a good idea necessarily, but you can use QPE, quantum phase estimation, and it will use fewer samples. But the circuit will have to be longer, so it will not be very friendly to NISQ devices. Okay, so QPE, because of the quantum Fourier transform embedded in there, you might have to do fewer operations, but in longer circuits. And with the Hadamard test, you might do more operations, but with shorter circuits. So pick your poison a little bit on how do you want to achieve that. So it looks promising, but there's a few pitfalls and there's a few caveats that can actually reduce the potential advantage. Oh, by the way, this is the quantum phase estimation will be quadratic. So you will have a quadratic advantage in all of your moments. So that means if I had to do it classically, and it takes 1 million samples, with Grover, with QPE, I can do it in the square root of 1 million. So that would be like 1,000. So that is definitely something that you would want to use a quantum computer for that sort of thing. I kind of want to move forward through this a little bit, I realized. Let me actually show you from the paper itself. One of the things the referee asked us to have a check on was, okay, so what good is this? What would you want to do? What would you want to get the moments of the PDE necessarily? So there is something called Dirichlet energy, and Dirichlet energy is essentially the integral of your solution. Well, the derivative of your solution with respect to x, you square it and you take the integral over the whole space. And this is definitely a moment because of the integration process. So I can recover this Dirichlet energy quadratically faster. And Dirichlet energy has many uses, for instance, in sub-mapping, machine learning, or even discrete differential geometry. Apparently, I was not aware of that. There's situations, for example, where your probability distributions will not have all of their moments defined. Maybe the skewness or the kurtosis or something like this that just don't exist. So there's another type of measure called the Sussman measure that can give you these averages as well. Then all kinds of quantum mechanical observables corresponding to Hermitian operators. If you go back to real time, you could definitely obtain them. Like if you're looking for energies, or if you're looking, like energies of a quantum system and so on and so forth, you can get them quadratically faster. And this is kind of my favorite reason. The central limit theorem will kick in, and most distributions, when you take independent identically distributions and you average them, they tend to go to the normal distribution. So if you have an educated belief that your distribution is only characterized by the first moment and the second moment, just the mean and the variance, then you might want to get those real fast with a quantum computer while you're doing the full distribution with a classical computer. There might be situations of industrial interest where that happens. And if you have two quantum devices, you can do them in parallel, one for the first moment and one for the second moment. So something to think about. Okay. Enforcement of the norm. This is the technicalities on how to keep the norm at L1, at L2, excuse me. So this is the ansatz that we use, by the way. We started on 6 qubits, all of them at the 0 position. Then this is called real amplitudes ansatz, because all of the gates are real, are wise. They don't have any complex numbers in them. The solution is real, so it makes sense to not get entangled with complex numbers if there's no need to. This barrier is just cosmetic. So we have the C0 gates here, and then there's a big C0 gate that makes the whole circuit be cyclical. Okay, so 1 leads to 2, leads to 3, 4, 5, 6, and 6 links back to 1. Okay, and then another sequence of RY rotations. Maybe let me show you the new plots that we obtain from here. So here's our, and you can repeat this. You can repeat this this block as many times as you want. If you do it sufficiently many times, you'll get into barren plateaus, and you get into like you won't be able to squeeze as much as you want from the circuit, but there's still something that you can obtain. So let's see what happens when we use, for example, 6 qubits. So 64 bases, 2 to the power of 6. Our initial state, we said, was a Dirac delta function. Okay, so at time t equals 0, we have a Dirac delta function. Then we do 2 evolutions, let's say, to 0.2, and we're going to solve this with 3 different systems. We're going to solve the same equation in 3 different methods. First of all, with Barkite in blue, with a quantum computer, simulated quantum computer. Then we're going to do it with classical Monte Carlo, and then we're going to do it with classical forward Euler, and we're going to compare how they stack up. So, and there's periodic boundary conditions, okay? So if one of these things were to hit the wall, it would come on the other side of the wall. Well, so essentially the shape is correct for most of them. And as time goes by, we realize with 6 qubits and the expressivity of our ansatz that at some time on the basis number 35, Barkite was not picking up this spike. Okay, so that was kind of called upon by the referee. Hey, by the way, you realize that you're overestimating here and here, but you're completely underestimating here and here and here. Okay, so that was initially not a good thing. And here's the comparison of the L1 norms. So these solutions are probability distributions, so they have to be L1 normalizable at 1. So if you look at forward Monte Carlo in orange, the answer is 1, as it should be. If you do a little bit of forward Euler, then you make a 5-6% error here. It means that your probabilities add up to 1.05 instead of 1. It's not great, but it probably has to do with periodic boundary conditions. But Barkite was reasonably good here. You know, it kept the L1 norm very close to 1. But we were very disappointed about this. So we decided to, okay, add more layers to the ansatz. So the ansatz is, let me see if I can get the ansatz again. Remember that I can add as many as I want. So this was with 1 repetition. So now I'm going to show you 2 repetitions so that you get an idea. So with 2 repetitions, there was more expressivity in the ansatz, and we started seeing that around basis get 35, Barkite was modestly trying to achieve a little bit of it. So it was definitely seeing something that it could not see with only 2 repetitions and 6 qubits. Okay, so still a little bit underrepresented, but okay. The problem was that the norm, we could not keep the norm normalized reasonably well. Maybe there's other ways of normalizing it other than the alpha term that I was presenting earlier. I don't know, it's open subject. At its worst point, or after 600 evolutions, the probabilities were not adding up to 1, they were adding to 1.16. So yeah, that's because you're trying to solve an L1 problem with a computer that can only solve L2 problems, right? So that's just a little artificial sometimes. So you have to work harder at maintaining this normalization, and it can remove from your quadratic speedups. Okay, so we decided to try how many it is? 3 layers, not 2 layers, 3 layers. Now I'm going to show you 8 layers, 8 qubits instead of 6, and I'm going to show you 5 layers. So there's 264 states, and the match was really good. I think all of the spikes were picked up. Here you can see some quantum noise. There should have not been any spikes here, but it's impossible to control. The error is a little bit larger, it's 1.22, but it happens earlier. Okay, it happens around 200 and 300 evolutions, and then it decreases very fast to very acceptable levels. So if you can work a little harder on maintaining the normalization, then you probably can make this, you can flatten this curve somewhere. All right, so these were the old plots. These were the old plots. So it's worth seeing again, what is it that we're solving? We're solving this differential equation with rho equals a third. Well, oh yeah, another thing. So this is a 2-dimensional plot. Here I am flattening, you know, for visual purposes, it's easier to see it as a flat line, but it's not a flat line. This is a surface of X and Y. So another way of seeing it is the Monte Carlo, let's say the classical solution is in orange and the quantum solution is in blue. It's not easy to tell one from the other. So what you do is you plot the difference, you know, and sometimes you make an error of like 2%. Up or down, up or down. It's kind of hard to say, and this is a typo here. So I prefer to view it linearly, but remember, it's not a curve, it's a surface. Okay, so there's some future work that I kind of want to do about this, and in fact, looking for collaborators. So if anyone's ever interested, please let me know. I took the first ansatz that came to mind that I had seen other researchers do in the literature, especially the Suguru Endo and the work of Kunasis. This paper is heavily based on a paper that I can tell you more about later on stochastic differential equations by Endo and Kubo. Why did I choose that ansatz and why did I not choose another ansatz? That's definitely open. What happens with barren plateaus? If you put just adding a lot of repetitions of the layers just does not always yield dividends. So there's a lot that you can say about these barren plateaus with Lie algebra. So that interests me a lot. Remove the dependency on the scaling. So instead of solving this in imaginary time with Barkite, I stands for imaginary time. Why didn't we do this in real time? So instead of a hit or imaginary time, let's do it with Schrödinger so that the normalization is kind of taken care of by itself. So that means that your SDEs, instead of being real, they will have to be imaginary. That's kind of really interesting. I kind of completed this with some of my colleagues at Deloitte actually recently. Rethink these variational methods with quantum adversarial networks, generative adversarial networks. I can show you a reference later when we upload it in the archive. So the application of these, there's different applications of differential equations are useful in many fields. The one I had in mind was finance. And can we use these for very exotic, very difficult, very computationally taxing derivatives or options, such as Asian options? I think the answer is yes. And the Feynman in Feynman-Kac comes from Richard Feynman, and there's a way to link this to Green's functions and Feynman path integrals and so on and so forth. That I can tell you more about at some other point. Can we link this Brownian motion to Feynman-Kac to Feynman path integrals? And what would it be? What would it be to do quantum computing not from a Hamiltonian point of view, but from a Lagrangian point of view? It's there's not too much literature on that, so that kind of really would be very, very profitable direction to look at, in my opinion. And with that, I thank you so very much for your time. I'll take any questions that you want now. Thank you.
Hey, thank you very much, Nicolas. From my side, I would really appreciate that the interactive session you did by putting, I really like that because it's more interactive, so you can really show the mathematical way, how it looks like, and the answers, etc. So thank you very much for that. And for the audience, is there any question you would like to highlight to Nicolas, please?
May I ask a question? It's
of course. Yeah.
Probably, please go forward.
Thank you so much for the talk. That was really interesting. It's just a question about I'm just trying to understand the Varkite method better. And these unitaries, so this set of unitaries that you have, you call them rotational parametric, these theta i's.
Oh, yes.
That were used to basically approximate the evolution of the Hamiltonian.
Yes.
I'm just trying to figure these, I mean, these are finite dimensional unitary matrices.
Yes.
Right? And what is their size? Because the Hilbert space in which your Hamiltonian is acting, that is a priori infinite dimensional. You're looking at some functions and everything.
Yes.
But when you're trying to approximate it by this Varkite method and by these unitaries, you're using some finite dimensional unitaries.
Yes.
I mean,
all
that's
the unity,
idea, I guess, of restricting to some finite dimensional Hilbert space inside the
right.
big Hilbert space and trying to do that.
So let me share the screen again. I was trying to see if I can find that, but I don't have it on this computer. The because I can make it even more interactive. I can show you how I produce those paths. So RY is a 2x2 matrix, and the C naughts are 2x2 also. So they're all, I mean, they're all 2x2. But you know, why didn't I add some topologies here? Why am I connecting it? This seems the most canonical way to connect it in this way, right? 1 to 2, 2 to 3, 3 to 4, 5, 6, and 1 to 6. But
so in this case, 6n is equal to 6. You're using 6 unitaries to approximate.
Yeah.
Acting on a qubit. So that's, I guess, for quantum computer, this is what you have to do.
Yes. Yeah. So we can go to the IBM quantum experience, and we could actually, all of them are available except this one. This one you have to kind of code it on your own. So that was kind of a tricky part, you know, because we had to do a little bit of trial and error until we got it right. But it's, I mean, it's just a matrix after all. But you're right about one thing. So the Hilbert space is infinite, right? But once you discretize, it's fine.
Right. I think you're looking at the evolution on the ground state, on this particular state, the 0, basically, and applying these unitaries to see how it will evolve under the Hamiltonian.
Yes.
So you're looking at the action of the Hamiltonian on this particular state, essentially.
Yes. Yes, I'm looking at the evolution of the Hamiltonian from a Dirac delta.
Right.
So this one I can manufacture easily because all of the states are at 0, and then I get a next gate to change a 0 to a 1. That's a really good question, because if it had been more complicated than this, If it had been a different quantum state, valid quantum state that is L2 normalizable, I would have had to use an optimizer. I would have had to use Covila, or I would have had to use some kind of something to find the angles that I need to feed in the first time. So if I have to, so here's where I have a philosophical problem with others. Said if I have to solve a very difficult classical problem first in order to feed it into a quantum computer, then the advantage is questionable. But here, I just have to pick where I want to have my X and put an X there to change it. Yeah.
Interesting. Cool. Okay. And to understand the thing better, so the more of these gates you use, the better you can approximate. So I was trying to understand this thing that you did to get Varkite to actually, bounce up and yeah, so these improvement in graphs basically.
Yeah, but
So
I don't know why. I don't know why. Yeah,
what
it's
is the
purely
physical process that you're doing? You're just applying the same unitaries again. It's the same circuit.
Yeah. I'm just repeating the block one more time. So here I said one time first, then 3 times, and then 5 times. But I think you're squeezing the lemon too much. I think after so many times, you get the barren plateau, and there will be nothing to squeeze anymore.
With this thing, I see.
I think, but it's empirical. I cannot prove it. I can just, my intuition tells me that if you repeat this 100 times, it might not be better than 5 or 7 times,
I see. And if you increase the number of initial gates, let's say from 6 to 10 and...
Yeah. So I first did, yes, that's a good question. So first I had 6, so 64 states. And then I did again 6. And I saw that there was some improvement. And then I was like 10. But yeah, because then you have more resolution. Right, the more qubits you have, the more resolution you have, and so on. But then you need more qubits, right? You need a more expensive machine. But again, I was very concerned about this. I was like, oh, the paper's gonna get rejected. This is just, But I just openly said, look, I don't know how to make the normalization better. And they said, okay, well, at least you tried. And I think this is the important thing in quantum, to admit when it is that you don't know how to do it any better, and you say it's open research. Can someone flatten the curve a little bit for me?
No, that's great.
Great question. Yeah.
And I mean, of course, so you've mainly concentrated on finance and different, well, SDEs coming from there. But I mean, there are so many. So this is very, very general. This applies to.
Oh yeah. So let me show you. There's the different manifestations, as I like to call it. So the Feynman-Kac formula, sphere, fine. So what I like to do is I like to start with something very general and not motivated too much, and then write it as a PDE.
Yes.
And then I can actually start making transformations to make this PDE look like a Schrödinger equation. The problem with the Schrödinger equation is that you're going to get a Hamiltonian. And this Hamiltonian has this, it has the differential operator here, the Laplacian, as it should be, but then it has some other function of x, and this will not be Hermitian unless these two commute, and they will not commute when this is a function of x.
Yeah.
So this, I mean, there's only so much that you can do with quantum mechanics. So I had a problem with that, but then as like special cases. So here's Feynman-Kac. There's your Feynman-Kac. Heat equation is this. Black-Scholes is this, Schrödinger is this one, then there's Fokker-Planck is also a special case of these, Kolmogorov is a special case of these, Hamilton-Jacobi, Ornstein-Uhlenbeck, because all of these are named stochastic processes that lead to different differential equations. Yeah, so perhaps that's the cool part of doing it like that.
Yeah. I mean, and just the fact that you can study the evolution of Hamiltonians, there should be applications in, I guess it's called quantum chemistry. So you can build Hamiltonians and just see how they evolve.
To see how they evolved. And again, you can only get the observables of these Hamiltonians, right? Energy states and this and that.
Yes.
It would be great if you could solve a full differential equation. But if you can get, for example, if the differential equation has a solution that is a probability distribution, and I give you 10 moments, can you recover the probability distribution from the first 10 moments? Or 5 moments, let's say. You know almost everything there is to know about it. So I argue that if you have 5 quantum computers and you get the first 5 moments, you have morally solve the differential equation in a way. Maybe, I don't know.
That's pretty cool. And I mean, if you have time, so if you can say, because it's extremely interesting, the some ideas that you have about applying Feynman's path integral
Right.
techniques.
So let me
Sum over all histories basically, and Feynman diagram.
Well, I got the idea from Wikipedia actually. It's when I say Feynman, I mean Feynman. I don't mean his brother or his sister, right? So I, like, okay, so Feynman-Kac formula, and here it is. Here's your PDE. Yeah, you can either solve it, or you can define this, and take a lot of things. Here's a partial proof, which, by the way, I also give in the appendix. And here they say, okay, yeah, so this PDE is like so, and it can be interpreted as a method for evaluating functional integrals, which is another way of saying path integrals. So path integrals have an imaginary part, and functional integrals are real. They're in Euclidean space. It's the connection between statistical and quantum mechanics. So if you have this Wiener measure here, like all of these things want to be like random paths in quantum, right? So I don't understand it very well. So I'm actually, that's kind of why I'm looking for someone to help me with that. But yeah, applications are quantum finance and quantum chemistry. So and I think those are the two winners of quantum, really, chemistry and finance. That's what I would concentrate. I would not concentrate personally. I would not concentrate as much on optimization and machine. And I know I get looks when I say machine learning, but I really think chemistry is where it's at. Let's see, it's path integral. So path integrals, yeah, where's the Feynman path integral? Yeah, it's got to be very similar to these things going on different paths. So that's what I was saying. You can do it with the Lagrangian instead of the Hamiltonian. Yeah, but I don't know the answers.
I see. And so these are basic questions. So if is the derivative of a stochastic process, so dWt, is that also a stochastic process itself?
Yeah, well, it's time. Well, the stochastic process cannot be differentiated, right? Brownian motion is just not differentiable.
Exactly,
so,
but you define some kind of dWt using
yeah.
I'm just trying to picture what that looks like.
It looks like time. It looks like time. Like so I didn't define it. I just kind of said informally. Because to define it, you need to go into stochastic integration and things like this, and it's a bit of a it's not something I know very well, by the way. It's kind of very advanced for me, at least, very advanced topic. So it is Ito's lemma, right? It says that if you take the differential of Brownian motion and you square it, it scales like time.
Yeah,
that's why I'll share my screen again if you don't mind. That's why I had to here I had to put a square root here because I'm going to square it and I'm going to divide it by 2. So in order to get a clean differential equation where I see an A, I have to do this. If I had done an A here, then I would see 1/2 of A squared. So it really is. I think I motivated it like informally and said here.
Yes.
Brownian motion is this.
Yes.
But I give plenty of references though.
Yes. No, it's just I mean, as you said, because it's not differentiable, and yet you define a differential. What does it mean, or what it captures?
So that differential is a short for an integral. There should be integrals on both sides, but it really is colloquial. And, it just says that if you are looking, I'll share my screen again. I hope I'm not oversharing my screen. What it says is that if you have a stochastic process, let's say d of x equals adt plus b dw, and if you are to square it, then this is all of this squared, So when you open up the square, you're going to have a squared dt squared, which is 0, because I said that dt times dt is 0. And then you're going to have 2 times AB dt dw, which is 0, because that's how I define it. And then I'm going to have B dw square. So all of this is, well, I guess with a square. It wouldn't work to get this right. So this will be equal to B dt. Yeah.
I see.
It's a way of manipulating these things. But so again, if I were to do it properly, I wasn't expecting a tricky question, you know.
That was
So the best way to the best way to do it would be with the stochastic integration, and then you would see everything in terms of integrals. I guess you would still see it with the differential here, right? But informally, it's something like that. Sorry, I'm at the edge of what I know here, you know.
I see. No, it's just well, in the Newtonian world, the derivative basically tells you, especially if it's with respect to time, it tells you how the function changes with time, or you can think of it as a vector coming out at that point and moving along. I mean, so I'm just wondering if in the stochastic world, what is the interpretation of this? It's giving you the rate of change of something with the time, or what does it try to capture?
Can I think about this for a minute or
Yes,
so before
absolutely,
I tell you something? Because I'm recorded, so I don't want to say something.
Yes. No, I think can be taken enough time from people. So
yeah.
Thank you so much. That was great.
No, you're welcome. You're welcome so much. I'll get back to you on that one.
Absolutely. Thank you so much.
Cool. Thank you.
Thank to you both for these minimum conference sessions. It's really great to have this here, honestly.
Cool.
So is there any further question you would like to ask? Yes. No. Okay, that's from the previous one. Is there any other question you would like to discuss with Nicolas? No? Are you sure? Okay, then I think we can close here. Nicolas, thank you very, very much for all, really. It has been very, very grateful, and I always learn one more thing, and it's the interactive way I will learn for you because I really like it. And yeah, thank you very much. Thanks to the audience to be here, and keep in touch. Get to you
Everybody
soon.
have a great day and a great weekend. Thanks again.
You
Take
too.
care.
Bye-bye.
Stay
Thank
safe.
you very much.
Bye.
Bye-bye.